The purpose of this lab is to use the principle of energy conservation and current conservation to predict and examine the behavior of various currents with resistors and capacitors. The loop rule and the node rule are rules that stem from the law of conservation of energy. Ohm's law will be needed for this experiment. The results of this experiment found that these laws are good at predicting the properties of ideal circuits. The system for this experiment will be various circuits. There will be no outside forces. We will assume that the resistance of the wires and ammeters are negligible, so the only contributions to the voltage will be resistors and batteries. Here's circuit 1. It's predicted that the current of I1 will equal I2. This is based on the node rule where the current into a junction must equal the current out of a junction. Comparing the calculated current to the ammeter's readings, the currents are equal. If one ammeter is replaced with a voltmeter, it will read 3 volts, while the remaining ammeter will read 0 amps. This is because the circuit is basically an open circuit with no current flowing through the resistors or the ammeters. After closing the circuit again, the voltmeter can be used to determine the resistance across various sections of wire. These resistance here have a potential of 0 because these are wires, because we are considering the wires to have no resistance, which means no voltage. It is predicted that for a full loop, the total potential would equal 0. When adding these values, the total potential is 0, which matches our predictions. This can be graphed, where we see the voltage decrease as we move through a loop of the circuit. When the 100 ohm resistor is placed in parallel with the ammeter, the current of the circuit increases. This is because the circuit will prefer the path of least resistance, to which the ammeter has no resistance. Circuit 2 is a circuit consisting of a light bulb of 2.2 farads, a 9-volt battery, and a 9-volt battery. By connecting and disconnecting the battery, the circuit can be made to charge and discharge the capacitor. When the capacitor is charging, the light bulb will start bright and quickly go out. The current will decrease towards 0 until the capacitor is charged. When the capacitor is discharging, the light will begin lit, but will slowly dim over time. The current will also decrease towards 0 until the capacitor is discharged. Here are the charging and discharging times for some different light bulbs with different resistances. The light bulbs with more resistance took longer to charge and discharge than the circuit. After setting up the previous circuit with a 30 ohm light bulb, I collected the data on the voltage over time. This relationship can be described by this equation, which can be linearized to this. RC is the time constant, or which the time at which the circuit is 1 over E of its original voltage. The RC can be determined through the properties of the circuit like this, or through the slope of the experimental data like this. Here they have the same value. The possible errors of this lab may be that this model assumes ideal circuits. Another possible error is human timing error. If this lab were done with real circuits and ammeters, we would find a lower current value as real ammeters and wires have some resistance to them, which would cause a decrease in the current of the circuit. If a real battery were used to charge the capacitor, it would take longer because the wires have some level of resistance. That's about it. See you.